aim is to find out these 2 points VIL and VIH. Okay, and then the corresponding VOL and VOH. So how do I go about doing that? Suppose I want to find these 2 points of intersection. What should I do? What region of operation is my NMOS and PMOS? Let's take VIL. NMOS will be in saturation, PMOS in linear. Now you write this equation out, then you have to differentiate it and equate the gain to -1. That's what we are doing here, right? We are finding the point at which the gain is -1. That is dV out by dV in equal to -1. Now the issue is that's a quadratic equation and stuff like that. It becomes very cumbersome to derive it. It is possible to do it with some approximation. So I would recommend you go back and just try it once. Okay, it's very much possible, but you just do it very carefully. Instead of doing all this cumbersome thing, there is another way where we can, with some approximation, obtain this expression pretty easily. Okay, I'll tell you what that approximation is right now. So finding VIL and VIH. Okay, let me draw it slightly exaggerated. Maybe this is not the right curve. Okay, the gain, this is my V in equal to V out line, and this is my VM comma VM. Now, if I find this straight line at this point at VM comma VM and I extrapolate it down, okay, this is the line passing through VM comma VM, okay, and the gain with slope G, which is equal to dV out by dV in at V in equal to VM. I am taking the line at V in equal to V out, finding the slope there and extrapolating the same thing with the same straight line with that slope. Okay, this will come and now meet my V out equal to VDD line. This is V out versus V in. This is V out equal to VDD. This I am defining as VIL. Okay. Similarly, on the other end, this comes here. Remember, I have drawn this little exaggerated just to point out. So, if you look at this, I am calling this as VIL and this as VIH. Actually, that point is going to be somewhere here because the line equal to slope of -1 will happen somewhere here. You have this much error, no doubt about it, but that error is actually very small. Okay, it's an approximation, but the error happens to be very small, and therefore it is possible to use this approximation quite well. Okay, any questions on the approximation? We are not doing it with the accurate expressions because that's a quadratic equation, becomes very complex. No, this is somebody has just found out and told you that okay, it works pretty well. So we are just using that, that's all. Okay, yeah, but it's like within like 5% apparently of the actual value, right? So now what do I need to do? I have to find dV out by dV in, right? This is my gain at V in equal to V out equal to Vm. Okay. So now what do? I have to go back and do the same story. IDSN equal to IDSP, right? So I'm going to say that the current IDSN is, let me use a short channel device for now, right? So this be Kn prime Wn by L into Vd sat n into V in minus Vt n minus Vd sat n by 2, right? This is V in near Vm. IDSP is what? Kp prime Wp by L Pd sat P into V in minus, no, this is not V in, this is V in minus Vdd minus Vtp minus Vd sat P by 2. Okay, I got to equate these two and then find dV naught by dV in. What is the problem in this? I equate these two currents by doing IDSN equal to minus IDSP. Then I have to find dV naught by dV in, and that is going to be minus 1. I mean, that is not minus 1, I'm sorry. That is basically the gain that I want. This is the gain that I want. Gain at V in equal to V out equal to Vm. Correct? I'm trying to find the slope of the VTC at V in equal to V out equal to Vm. That's what I'm trying to do. What is the problem in this equation? Can you find the slope here? Look at the current equation. How do you do dV out by dV in here? Yeah? What's the issue? There is no V out. There is no V out in this, right? And therefore, if you do not consider the channel length modulation, you cannot get this exact expression. Okay, so we will come to what happens when there is no channel length modulation later. Okay, so therefore what I'm going to do is I'm going to say that IDSN is whatever this expression IDSN prime into 1 plus lambda V naught. IDSP equals IDSP prime into 1 plus lambda n lambda p V out minus VDD. Okay. Agree with me here? So now you can go ahead and find dV out by dV in. The gain is at this point at V in equal to V out equals Vm. Okay. So I'm not going to spend my time deriving that here because the algebra is it's easy, but it's just cumbersome. It turns out that you can derive it to be exactly like this. The gain, okay, I'll just write that here. It turns out the gain is, maybe I can just turns out the gain is as follows. Okay, you can derive this later, it's there in the tutorial for you to derive this expression. Okay, I've tried it out, it comes out correctly. Okay, you just have to do it carefully. I'm just not wasting my class time for this. So the gain is, if you look at it, is basically proportional to 1 by lambda n minus lambda p. So if the technology is symmetric and all PMOS parameters are negative of NMOS parameters, what will be the gain? That is what you should be very careful about. Lambda p is also a negative number. So this doesn't mean that if lambda n and lambda p are minus of each other, so if lambda p is minus lambda n, then gain is actually proportional to 1 by 2 lambda n. So the fact that the gain is very high comes from the point that channel length modulation parameter itself is very small, and therefore the gain will be very high. It's not because lambda n minus lambda p is almost 0. Clear? Okay. So with this expression, can you now tell me what VIH and VIL should be? Okay, let's just go back and redraw this thing. V out, V in. So what we have said is, now the approximated VTC is going to be like this. It's a straight line. This is VIL. This is VIH. This line has a slope of G equal to G, which is given by this expression. Okay, and the line also passes through Vm comma Vm. Okay, now it's just a question of slope. Can you find out VIH and VIL from this? Please do it. G is positive or negative? Negative slope. It's a large negative number. So Vm minus, so the point is VIH should be to the right of Vm. Correct? It should be Vm plus some number. Does that happen? Yeah, Vm minus Vm by G. G is a negative number. So that actually becomes a greater than Vm. So I think we are right. Okay. What about VIL? L equals Vm minus VDD by G. Yeah, Vm plus VDD minus Vm by G, and we'll come back to that. So are you able to get this? First point, suppose G were infinity. What will happen to VIL and VIH? Both of them will just collapse to Vm. That's the ideal case. If the gain is such a sharp transition, right, where V out and the VTC becomes a straight line at the trip point, then both VIL and VIM will simply collapse and come down to Vm. So anything greater than Vm is logic high, anything less than Vm is logic low. Okay. So with this, we will actually proceed in the next class to do the noise margin analysis. Now we want to figure out, okay, if my input is at VIL, then how much noise can it tolerate before it goes into some indeterminate region or the output will switch. So how much noise can we tolerate for both logic levels is what we are going to look at in the next class, and that's the noise margin that I spoke about in the beginning of the class.